We'll start in 1 minute. Today we'll be in section 11.9, representations of functions as power series. And a reminder, test 4 will be 1 week from today, and it will be over chapter 11, sections 1 through 9. Okay, in section 9, we start, it is useful in practice to be able to represent certain types of functions as sums of power series. So we know that for the absolute value of x less than 1, 1 plus x squared, and so on, is a geometric series. And when the absolute value of x is less than 1, the sum is 1 divided by 1 minus x. So x is a variable, but x is the common ratio for this geometric series. And so it converges to 1 over 1 minus x. So in other words, the function f of x equals 1 over 1 minus x can be written as the sum of a power series, which is that geometric series. And then just a note, the partial sum S sub n is 1 plus x squared up to plus x to the n. I think I said that wrong. 1 plus x squared plus dot 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 plus x to the n. The nth partial sum is just a degree n polynomial function. Okay, so as a template, we're going to use the fact that 1 over 1 minus x equals 1 plus x squared, and so on, to write the following functions as sums of power series. And we'll also find the radiuses of convergence and intervals of convergence also. Okay, so our first one, f of x equals 1 divided by 1 plus x. So we rewrite this as 1 over 1 minus negative x. So in this power series up here, this 1 over 1 minus x equals 1 plus x squared, and so on, we're going to replace x with negative x. And we'll get 1 plus the number negative x, to, or the term negative x to the first, plus the term negative x to the second, plus the term negative x to the third, and so on. So when we evaluate each of those, we'll get 1 minus x plus x squared minus x to the third plus x to the fourth, and so on. And then using the sigma notation, we'll get 1 over 1 plus x equals the sum from n equals 0 to infinity. Well, this is alternating, so we have negative 1 to the n times x to the n. Okay, so for this one, in this denominator, we had 1 minus negative x, so the absolute value of negative x. Since we wrote it as a geometric series, the absolute value of negative x is less than 1. But the absolute value of negative x is just the absolute value of x, which is less than 1. So the radius of convergence is 1, and the interval of convergence is the open interval from negative 1 to 1. So make note of that, interval of convergence. From negative 1 to 1. Okay, so you can probably tell me what to do for the next one. We want to find a power series representation for the function. It's just a rational function, 1 over 1 minus x squared. Maybe it seems a little weird to you, but all we're going to do, we're using this as our template, 1 over 1 minus x. 1 minus, quote, x is 1 plus x squared plus dot, dot, dot. So for this function, 1 over 1 minus x squared, x squared is going to take the place of x in this power series representation. So this is going to be 1 plus x squared to the first plus x squared to the second plus x squared to the, x squared to the third, and so on. So we'll simplify those, and we get 1 plus x squared plus x to the fourth plus x to the sixth, and so on. And then in sigma notation, 1 over 1 minus x squared is the sum from starting at n equals 0 to infinity. And it's not alternating, so it's just going to be x to the 2n. Here, the expression that took the place of x in our template for a geometric series is x squared. So x, the absolute value of x squared is less than 1. But if the absolute value of x squared is less than 1, then the absolute value of x is less than 1. So the radius of convergence is 1. The interval of convergence is from negative 1 to 1 again. Okay, for the next one, find a power series representation for 1 over 1 plus x squared. So a hint is we'll sort of combine what we did in the previous two, certain things about what we did in the previous two examples to get a power series representation for 1 over 1 plus x squared. Okay, up here is what I'm referring to as a template. 1 over 1 minus some expression in the variable x equals 1 plus that expression in the variable x plus the expression in the variable x squared, and so on. Okay, the first thing I'm going to think of or write, I'm going to think of 1 over 1 plus x squared as 1 over 1 minus the term negative x squared. So we're in agreement that those are equivalent, right? Okay, then similar to what we did in the very first one, where we replaced 1 plus x with 1 minus negative x, and then it was the term negative x that was raised to those powers. This time it's going to be the term negative x squared that's raised to powers. The first term, though, is 1, and then plus the term negative x squared to the first, then plus the term negative x squared to the second, and so on. So I'll write the next one plus the term negative x squared to the third, and so on. So we evaluate each of those. We get 1 minus x squared, and this will be plus x to the fourth. The next one will be minus x to the sixth. The one after that is going to be plus x to the eighth, then minus x to the 10th, and so on. Okay, so this function, 1 over 1 plus x squared, using sigma notation, we start from n equals 0 to infinity. So what comes next? So it's an alternating one. We alternate between minus, plus, minus, plus.
Negative 1 to the n.
Yeah, so we'll have a negative 1 to the n. And then the terms,
X to the 2.
yeah, x to the 2n. So if you're ever in doubt about your summation, you can test it out. So we can test a couple of terms. When n equals 0, negative 1 to the 0 is 1. X to the 0 is 1. So that works when n is 0. Then when n is 1, negative 1 to the first is negative 1. X to the 2 times 1 is x to the second. That agrees with our second term, minus x squared, and so on. Okay, the next one's a little more involved, but we are going to end up doing the same sort of thing that we've been doing so far. I probably should have left myself more space for this one, but hey, we're going to think of 1 over x plus 2. First, think of it as 1 over 2 plus x. And then 1 over 2 times the quantity 1 plus x over 2. And then this is 1 over 2 times the quantity 1 minus negative x over 2. And for now, we'll just multiply 1/2 times 1 over 1 minus the term negative x over 2. Okay, so inside the brackets, 1 over 1 minus the term negative x over 2, we're going to find a power series representation for this the same sort of way that we've been doing already. So we have 1/2, and then the power series representation for this, 1 over 1 minus some expression in the variable x. We'll have 1 plus the term negative x over 2 to the first, plus the term negative x over 2 to the second, plus the term negative x over 2 to the third, and so on. So we'll write it out a little bit. Evaluate each of those. So we get 1/2 times the quantity 1, negative x over 2 to the first. If we add that, we can write that as minus x over 2. Then we're adding the term negative x over 2 squared, so this will be plus x to the second over 4, but I'll just write it as 2 to the second. Then the next term, when we raise the term negative x over 2 to the third, we get negative x to the third over 8, but I'll write it as minus x to the third over 2 to the third, and so on. Okay, so next thing I'm going to do is one of two things, and I haven't decided which way I'm going to do it yet. So I'll just pick one. I guess I'll leave the factor 1/2 out and then write this expression inside the brackets using sigma notation. So it's 1/2 times the sum, starting at n equals 0 to infinity. The terms alternate from addition to minus to addition and so on. So we have to have a negative 1 to the nth in this case. And what are the terms? Yeah, so x to the n over 2 to the n. You can see that the exponents on x in the expansion match the exponents on 2. Right? Okay, but we can multiply each one of those terms times 1/2. So we could have done that earlier. I could have multiplied 1/2 times this quantity and then write the sigma notation, but it works doing it in the other order. We just multiply every term by 1/2 and we get this sum starting at n equals 0 to infinity. We still have -1 to the n. X to the n stays the same. But when I multiply 2 times 2 to the n, I get 2 to the n plus 1. Okay, so for this one, it was this -x/2 that took the place of x. Oh, you can't see it. But anyway, to find the interval of convergence, we take this quantity, -x/2, put it in absolute value. The absolute value of -x/2 is less than 1, but that's equivalent to the absolute value of x/2 is less than 1. Multiply both sides by 2. The absolute value of x is less than 2. So the radius of convergence is +2, and the interval of convergence will be the open interval from -2 to 2. So this is the interval of convergence. Okay, let's move on to the next page. The next level. Find a power series representation of f of x equals x to the second divided by 1 plus x to the second. Hey, we're going to use what we already know about the power series representation for 1 over 1 plus x to the second. Okay, so we're going to think of this as this x squared over 1 plus x squared. Think of that as x squared times 1 over 1 plus x squared. So I'll look on the other page. We did the 1 over 1 plus x squared. So I haven't got all of these memorized yet. So 1 over 1 plus x squared, the power series expansion for that in sigma notation, the sum from n equals 0 to infinity, -1 to the n times x to the 2n. So if you write out the first few terms, this is 1 minus x squared plus x to the 4th minus x to the 6th, and so on. So we're just going to multiply each of those terms by x squared to get the power series representation for x squared over 1 plus x squared. So x squared over 1 plus x squared. Just multiply each of the terms by x squared. So I'll write what the expansion will be. If we multiply each of those terms by x squared, we get x squared minus x to the fourth plus x to the sixth minus x to the eighth, and so on. Or if you want to make the change in the sigma notation first, you can. When I multiply x to the 2n by x to the second, what do I get? X to the 2n plus 2. So this is just okay. So what I did was I multiplied x to the second times x to the 2n, where n is any number from 0 to infinity. And then a property of exponents. If you multiply two terms that have the same base, you add the exponents. But it's a little more conventional to write it as the exponent is 2n plus 2. This is okay if you want to do it that way, but hey, so this is nice to know. If you know what the power series representation is of some function that is a multiple of another function, all you have to do is multiply the new function times the power series representation of the other. It's pretty nice. So when you're working on the textbook exercises, just watch out for that. You can take a fairly simple problem and spend 2 hours on it when it should only take 5 minutes. Hey, the next one, use a partial fraction decomposition to find a power series representation for f of x equals negative 2 over x squared minus 1. Okay, negative 2 over x squared minus 1, this is negative 2 over x plus 1 times x minus 1. So if we write it using a partial fraction decomposition, we can say that this is equal to some number a divided by x plus 1 plus some number b divided by x minus 1. And we want to find the values of a and b. Okay, so a over x plus 1 plus b over x minus 1 is a times the quantity x minus 1 plus b times the quantity x plus 1 all over x plus 1 times x minus 1. And so the a times x minus 1 plus b times x plus 1 has to equal negative 2. So we'll expand this. A times x plus 1 is ax minus a, and then plus bx plus b. This has to equal negative 2. Okay, so we have ax plus bx. We'll write that as the quantity a plus b times x. And we have minus a plus b. So minus a plus b. This has to equal negative 2. since negative 2 doesn't have the variable x, the coefficient of x here has to be 0. So a plus b has to be 0. And negative a plus b is negative 2. So negative a plus b is negative 2. When we add these two equations, a plus negative a is 0, b plus b is 2b. 0 plus negative 2 is negative 2. So we get b equals negative 1. And that means a has to be positive 1. Okay, so our two terms then, if a is 1, we have 1 over x plus 1. And we can write this as plus negative 1 over x minus 1. So we want to use the sum of these two rational expressions to help us find a power series representation for negative 2 over x squared minus 1. Okay, so any ideas? So a little bit earlier, we found a power series representation for 1 over 1 plus x. 1 over 1 plus x is the same as 1 over x plus 1. So we did find a power series representation for 1 over x plus 1. And anything else that you notice? If I multiply this second rational expression by 1 in the form negative 1 over negative 1, I'll get 1 over 1 minus x. And we know what 1 over 1 minus x is. So let's think of this as 1 over 1 plus x, and then plus 1 over 1 minus x. So the power series representation for 1 over 1 plus x I'll write out the first few terms of that. 1 over 1 plus x. They're 1 minus x plus x squared minus x to the third, and so on. We add that to the power series representation of 1 over 1 minus x. This is the one that we should remember. 1 plus x squared plus x to the third, and so on. Then if we add these series term by term by combining like terms, what are we going to get? Yeah, half the terms cancel each other out. The other half gives us 2. So 1 plus 1 is 2. Negative x plus x is 0. X squared plus x squared is plus 2x squared. Minus x to the third plus x to the third is 0, and so on. So we get 2 plus 2x squared plus 2 times x to the fourth plus 2 times x to the sixth, and so on. So we can write our original function, negative 2 over x squared minus 1 is the series starting at n equals 0 and going to infinity. So what are the terms?
Two x to the 2n.
Exactly, 2 times x to the 2n. So this time x to the absolute value of x to the second is less than 1, which just means x squared is less than 1. But that's equivalent to the absolute value of x is less than 1. So the radius of convergence is 1, and the interval of convergence is the open interval from -1 to 1. All right, now the theorem. This theorem will help us take us to the next level. So if the power series, the terms have a coefficient c sub n multiplied by the binomial x minus a to the n, if it has radius of convergence capital R greater than 0, then the function f of x, which is just the power series, it's differentiable and continuous on the interval from a minus r to a plus r. And the derivative of f of x can be found by computing the derivatives term by term from the power series. And the integral, the indefinite integral of f of x, first remember the constant of integration c, and then plus the term by term antiderivative of each of those terms from f of x. Okay, the radiuses of convergence of the above power series are both capital R, but the intervals of convergence may or may not include the endpoints. Differentiating and integrating term by term in a series works, provided that the series is a power series. And it is not as simple for other types of series. Okay, let's see how we do on this next example. Find a power series representation for f of x equals the natural log of 1 plus x over 1 minus x. Using one of the properties of logarithms, so I hope I don't run out of space. So the natural log of 1 plus x over 1 minus x is the natural log of 1 plus x minus the natural log of 1 minus x. So this is our f of x. So let's take the derivative of f. what's the derivative of the natural log of 1 over x? Or sorry, oops. What's the derivative of the natural log of 1 plus x?
1 over 1 plus.
Yeah, 1 over 1 plus x, and then we subtract the derivative of the natural log of 1 minus x. The derivative of the natural log of 1 minus x is negative 1 over 1 minus x. Right? Are we all in agreement? And then 1 over 1 plus x minus negative 1 over 1 minus x. Oh, I'll just write it over here. This is 1 over 1 plus x plus 1 over 1 minus x. Okay, so what are we going to do? We want to find a power series representation for the natural log of 1 plus x over 1 minus x. We computed its derivative and found that the derivative is 1 over 1 plus x plus 1 over 1 minus x. So we know the power series for each of those, 1 over 1 plus x and 1 over 1 minus x. So we're going to add them, add the two power series together. And then what? After we add the two power series for the derivative, what should we do? Okay, so if I word it a little differently, we're going to find a power series for f prime of x. How do we use that to find a power series for f of x? We're going to take the integral of the f prime of x power series, term by term. Okay, so we did both of those, or we know both of those. So this was the previous example, wasn't it? 1 over 1 plus x plus 1 over 1 minus x. So what did we get? We got, if we write it out, 2 plus 2x squared plus 2x to the 4th plus 2x to the 6th and so on. That was the previous example. All right, so the power series for f of x. Well, we're just going to term by term find an antiderivative for each of those. So we include the constant of integration c, and then find antiderivatives. So 2x plus 2x to the 3rd over 3 plus 2x to the 5th over 5, and so on. 2x to the 7th over 7. Okay, so using the sigma notation for the power series, the natural log of 1 plus x over 1 minus x equals c plus the sum of something. So it looks like we can start n at 1 in this one. Right, I might change my mind, but let's see how it goes.
2x to the n divided by n.
Well, the exponents differ by 2. So let's see. Two times x to the 2n minus 1. I think that works. When n is 1, 2 times 1 minus 1 is 1. When n is 2, 2 times 2 minus 1 is 3. Yeah, I think this will work. And then the denominator is also 2n minus 1. So are we all in agreement? Hey, let's determine what the value of c is. Well, if we replace every x with 0, when x is 0, we get the natural log of 1 plus 0 divided by 1 minus 0, which is the natural log of 1. And when we replace every x with 0, the only thing left on the left or on the right hand side is c, but the natural log of 1 is 0, so c is 0. So we update this and write the natural log of 1 plus x over 1 minus x is just this power series. Okay, one more. Find a power series representation for g of x equals 1 over the binomial x plus 1 squared. What should we do this time? I guess we better hurry. There's less than 3 minutes left.
Are we going to just multiply the series, two series together? Since we know.
Oh my goodness. You can multiply series, but there might be an easier way. Note, if f of x is 1 over x plus 1, we know what the power series expansion is for 1 over x plus 1. Then what's the derivative of f of x?
Is it g of x?
So we can use the quotient rule for the derivative. The derivative of 1 is 0 multiplied by the denominator x plus 1. And then we subtract the numerator multiplied by the derivative of the denominator, which is 1, divided by the square of the denominator. So this simplifies to negative 1 over x plus 1 squared. So this gives us a hint. If we assign a function capital F of x to be negative 1 over x plus 1, then the derivative of that is positive 1 over x plus 1 squared. So we can find a power series expansion of negative 1 over x plus 1 if we just multiply -1 times the power series expansion for 1 over x plus 1. Then after we find this power series expansion, we take the derivative term by term to find the power series expansion for 1 over x plus 1 squared. So I haven't run out of time yet, so this is -1 times, see, 1 over x, 1 plus x, that's 1 minus x plus x squared minus x to the third, and so on. That's the power series expansion. So the power series expansion of this, multiply this by -1, we get -1 plus x minus x squared plus x to the third, and so on. And then just take the derivative of every term, and that will be the power series expansion for our original function, 1 over x plus 1 squared. Okay, but we're out of time for today. So on Monday, we'll look at more stuff from section 9, plus possibly some other stuff from chapter 11. Yeah.